For today's lesson, we're going to talk about a very important differentiation technique called chain rule. And what the chain rule is it provides a way to take the derivative of a composition of functions. So before we get to the calculus of this lesson, let's take a step back and do a little review of pre-calculus, because this is very important. So go back and think about the term function composition, a topic you learned in pre-calculus. And two main types of function composition are the two most talked about. Of course, you can do any type of function composition, but the two most talked about are just simply what we call Fogg and Goff. And Fogg and Goff, Fogg is simply the composition of G inside of F, and Goff is the composition of F inside of G, as you can see on the screen. Let me give you a more concrete example. Let's say that I had two functions. Let's say that f of x was equal to sine of x, and let's say that g of x is equal to x squared. If I wanted you to find the composition of those two functions, specifically Fogg or f of g of x, then that would mean I would want you to take the g function and substitute that into the f function, thereby giving you a new function, namely sine of x squared. And so that's function composition, taking one function, and if you notice, you do see the x squared function inside of the sine of x function. Well, the question remains, though, in the terms of calculus, how would you take the derivative of such a function, right? You can't just, the only rules that we've learned thus far are simply basic rules, like the derivative of sine is cosine, or the derivative of x squared is 2x. But we haven't had a rule, technique, of finding the derivative of the composition of functions. And this is how you do it. Derivative of f of g of x. So in other words, whenever you have a function inside of another function, or in other words, composition, chain rule applies. And what you do is you take the derivative of the outer function times that by the derivative of the inner function. And I know that looks really weird, and what are you talking about, outer and inner function? Well, let's go back to this function right here. Like if we said that f of g of x is sine of x squared, it might not look like it, but what I would classify as the outer function would be sine of x, is that right? And then the inner function I would classify as x squared, because the x squared function is inside of the sine of x function. So that's why I classify as outer and inner. So if I use this rule, derivative of f of g of x for this particular problem would be the derivative of the outer function, which we already said was sine of x. So the derivative of sine of x would be cosine of, notice it says the derivative of the outer function with the inner function still inside of it, so it wouldn't just be the derivative of sine of x. Well, the derivative of sine of x is cosine, but it wouldn't just be cosine of x, it would be what that inner function is, which is x squared. So derivative of sine of x squared would be cosine of x squared times, and now go back and take the derivative of the inside function, derivative of x squared would be 2x. And if you, that's great, that's actually the answer, but if you want to just rewrite it, you could say that's simply 2x cosine of x squared, and that would be the derivative of that function composition you just seen. All right, what we're going to do is let's take a look at some other examples. So let's go ahead and try another one. So let's say that I gave you the function of 3x minus 2x squared to the third power. And if you notice, this would be chain rule, because you can clearly see that there is a function inside of another function. And let me prove that to you. The 3x minus 2x squared is inside parentheses. So there you go right there. Something is inside of something else. So ding, 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 function composition, ding, 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 chain rule. The outer function, if you notice, is the stuff that's outside the parentheses, which is the value q, power of 3. So this is a function composition where I have the 3x minus 2x squared inside of this quantity cube. So its derivative would simply be take the derivative of the outer function, which is this case, which in this case would be, yes, I have a cuckoo clock home. Okay, which would be the derivative of this, derivative of a quantity cubed. Remember the power rule applies here. Bring the power down, so that would be a 3. Keep the quantity alone, remember, because that still stays. It's the derivative of the outer function in terms of the inner function, so that still stays there. So that would be, drop it down to power, so that's squared. Remember, that's stemming from, let me go over here, remember, that's stemming from the power rule. If you had x cubed, the derivative of that, if you had x cubed, the derivative of that, or derivative of x cubed, shouldn't have gotten that close to the order. Derivative of x cubed would be 3x squared. So that's where this is coming from, the 3 and then the quantity inside of there. All right, and then now, don't forget, you have to go back and take the derivative of the inner function. And so when we take the derivative of the inner function, then you're just, the inner function is the 3x minus 2x squared. And so the derivative of that would simply be, and I'm going to use parentheses so it doesn't all be together. So that would be 3, and then that would be minus 4x. So that would be the derivative of the inside function. And in reality, guys, that's actually a very good stopping ground, because if I wanted to evaluate my derivative at a point, I could just simply plug in whatever number I want. So I'm just going to leave it right there. Of course, you could do a little algebra and clean this up, and you would end up getting, let's see, 3. I'm going to distribute that. 3 times 3, so that's going to give me 9. 3 times negative 4, that will give me negative 12x. So that's that part, and then 3x minus 2x squared. So then that will be my derivative. Again, though, this is a legitimate answer. It's just that this is a little bit more simplified for that. All right, and so that would be an example for that problem. All right, let's take a look at another one. So I'm just going to open up a new page, and let's say that I give you the function of f of x equals to x, and then I say that that I have the function cube root of x squared minus 1 squared. All right, and so let me do that a little bit better so you can see it a little better. This is the cube root. All right, let me try again. All right, let me draw 3. Okay, that's better. Okay. All right. Now, so there's my function. Now, as it's written, you obviously see that there is a function inside of another function. So you could, if you notice, you might argue that there's x squared minus 1 is in squared, and then that is all in the cube root. Clearly, this is a function inside of another function, so definitely function composition applies here, so the chain rule applies here. Now, again, remember about the basic derivatives we've learned. We haven't learned how to take the derivative of a radical. What we have learned from pre-calculus is how to rewrite a radical in terms of a power, a rational exponent. And what that means is I would rewrite this as simply x squared minus 1 to the 2/3 power. And that looks really rough, so let me try that again. The 2/3 power. So that would be to the 2/3, still looks rough. No, 2/3 power. I don't want to come up. There it is. That's my 2/3. Anyway, so again, we haven't done the calculus yet. That's just using pre-calculus to rewrite it. Now let's take the derivative, because now you can clearly see there's this function, x squared minus 1, inside of 2/3 function. So then its derivative would simply be the derivative of the outer function, which in this place is the power of 2/3. So then that derivative would be 2/3. Keep the inner function alone, And then remember the power rule says subtract 1 from that, so 2/3 minus 1 would be negative 1/3. And then now go back and take the derivative of the inside function, and the derivative of the inside function would be 2x. And again, that is a legitimate answer. If you wanted to just clean that up a little bit, just so it would look a little bit more presentable, maybe if it was a multiple choice question on the AP exam, then what I would do is remember that this is a negative exponent, so it goes down to the bottom. So I would have 2 times 2x, that would be 4x. I'd have 4x over 3, and in the bottom, in the denominator, I'd have x squared minus 1, and then now positive 1/3 power. It's supposed to be a 1/3, guys. I don't know why the pen's not working like it should. You gotta love technology. 1/3. The 3 is just not wanting to come up like it should. The 3. There it is. 1/3. Still looks horrible. Anyway, that is supposed to be a 1/3. I'm gonna get it eventually. 1/3. Okay. All right, and that's parentheses now. Oh my goodness, I hate this pen. All right, so that would be 4x over 3 times x squared minus 1 to the 1/3 power. All right, let's take a look at another one. Let's say that I gave you a new function, and let's see if the pen wants to cooperate this time. So here's your new function. F of x is equal to negative 7 over 2t minus 3 to the second power. Now, when you see this, you're probably thinking, oh, I got a quotient, so I could use the quotient rule. Well, that's true. You could do that. But instead, what I'm going to do is I'm just going to rewrite this with a negative exponent. So I'm just going to say f of x is equal to negative 7. And then I'm going to bring this whole quantity up. So 2t, that should be a t if that's f of x. So maybe this should be f of t. F of t. All right. 2t minus 3 to the negative 2. So now I won't have to use the quotient rule. I can just simply use the chain rule because I have a function inside of another function, negative 2. So the derivative of this, and keep in mind that 7, that negative 7 in front is just a coefficient. So the derivative of this would be the derivative of the outer function, which is that power, negative 2. So negative 2 times negative 7, that would be 14. Keep the inner function alone. Subtract 1, so that gives me negative 3. Now go back and take the derivative of the inside function. The derivative of the inside would be 2t minus 2 would be just 2. And that's a good answer, but then if I just wanted to clean it up a little bit, I would say 14 times 2. So I would 28, and then 2t minus 3 to the negative 3rd power, or you could write that as simply 28 over 2t minus 3 to the 3rd power. And that would be the derivative of that function. Obviously, guys, these problems can get a little bit more complex. So if you wanted to look at another one, let's say that I had f of x is equal to x squared times the square root of 1 minus x squared. I'm going to ask you to take the derivative of this. I will have to use the product rule because notice that I have this function x squared times this function, which is the square root of 1 minus x squared. And remember, I have no rule for the derivative of a radical, so I'm just going to rewrite that as a power, so I can use the power rule. So x squared, and then times, this would be the quantity, 1 minus x squared to the 1/2. And so not only do I have to use the product rule, but I'm also going to have to use the chain rule, because for this value over here, notice I've got a function inside of another function. So here's what I'm going to do. I'm going to do the product rule first. I'm going to have to do the product and the chain rule at the same time. So first, so x squared, I'm going to put that in parentheses so I don't lose anything. First, this is a very, very bad pen. Do not buy a Lenovo. These are horrible. All right, first times derivative of the second. So the derivative of the second is the chain rule, so I'd have 1/2, and then keep the quantity inside, subtract 1 from the exponent. Now go inside and take the derivative of the inside, which would be negative 2x. So that's first times derivative of the second, plus second, so 1 minus x squared to the 1/2, times derivative of the first, which would just be 2x. That technically is my derivative. Now, everything else beyond this is going to be algebra, where I try to simplify and clean this up. What I'm going to notice is I do have GCF of 1 minus x squared, and you take out the smaller, so I'm going to take out the negative 1/2 power of that. So I'll factor out 1 minus x squared to the negative 1/2, divide that out, and what gets left behind is, let's see, 1/2 times x squared is 1/2 x squared times a negative 2x. So that would give me negative x cubed. So I'd have negative x cubed, and then plus, and here's what gets interesting, if you factor this negative 1/2 power out, and this is already a 1/2 power out here, remember, when division, you subtract your exponent, so half minus a negative 1/2, technically a whole. So that means you're left with 1 whole unit of that term. So that leaves behind 1 minus x squared times 2x. And I'm still going to clean this up, so I'm still going to have the 1 minus x squared to the negative 1/2 out here. I'm going to have negative x cubed. I'm going to distribute this, so that gives me plus 2x minus 2x cubed. Almost there. So then what I'm going to be left with is in the numerator, I'm going to have negative 3x cubed, so negative 3x cubed plus 2x over, in the denominator, I'd have 1 minus x squared to the positive now, 1/2. Or you could write that as a square root, but there would be derivative of that function, negative 3x squared plus 2x over the square root of 1 minus x squared. And so, again, this took not only the chain rule, but also the product rule to do this problem. All right, let's take a look at another one. So if I did f of x, let's say I gave you the function f of x equals to x over the cube root. I do not like this Lenovo, for the record. So the cube root of x squared plus 4. Again, I would rewrite this, because I really don't want to use the quotient rule. I would rewrite this. I don't have a rule for a radical, so I'd rewrite this as x times x squared plus 4 to the 1/3 power. It's the same thing as the cube root of a quantity. Even more so, notice I'm going to have to use the product rule for this, and so the product rule, I'd have first times derivative of the second, which would be 1/3 x squared plus 4 to the negative 2/3. Now I go back and take the derivative of the inside, which would be 2x, plus second, so x squared plus 4 to the 1/3 times the derivative of the first, which would just be 1. That's your derivative, but if I wanted to clean it up, I notice I'd take out my common factor, which in this case would be x squared plus 4, but take out its lowest term, which would be negative 2/3. Okay, negative 2/3. Pen just doesn't want to catch it. All right, there it is. And then that would leave behind 1/3 times 2, so that would leave me 2/3 x squared. Then again, 1/3 minus negative 2/3, losing 1 whole unit. So that'll leave me x squared plus 4. And then, I'm just going to combine the numerator. 2/3 x squared plus 1 x squared would give me 5/3 x squared plus 4 over, this would give me just x squared plus 4 to the 2/3, which is a great answer, but one other thing, if I wanted to clean this up even more, is I could, so that there's not 5/3 in the numerator, I could just multiply the numerator and the denominator both by 3. So let me show you what I mean by that. Like multiply the top numerator and the bottom by 3, and so that would give me simply 5x squared plus 12 over 3 times x squared plus 4 to the 2/3. And that would be my answer for that problem. All right, last one we're going to look at for today. A lot of notes, right? So f of x is equal to, let's say I have the function 3x minus 1 over x squared plus 3, and it's that quantity squared. I know I have been trying not to use the quotient rule, but unfortunately I don't have a choice now. Well, I mean, I guess I do. I mean, I guess I could simply square both terms and move that one up. Yeah, I could do that. That's legitimate. But you know what? I'm just going to break down and just go ahead and try and use the quotient rule this time. But still, I have this function inside of the squared, so its derivative would be the chain rule. So the derivative of this would be in the power down 2, leave the quantity alone that's inside, so that gets left alone, and then drop the power down to 1. But now I've got to take the quotient rule. So then it'll be low d high. Low d high minus high d low all over. So move this would be low, so x squared plus 3 low d high, which would be 3, minus high d low would be 2x all over low squared. So that would be x squared plus 3 squared. So there's the derivative of that, which is perfect. Everything else beyond this is going to be algebra, so I'm just going to leave it to you to try to clean this up. But here's what you would end up having. You'd have 2, and then 3x minus 1, and then up here you'd have 3x squared plus 9 minus 6x squared plus 2x over x squared plus 3 cubed. And then if I really wanted to just be a really star student and clean it up finally, I'd get 2, 3x minus 1, and then inside of there I'd get negative 3x squared plus 2x plus 9 over x squared plus 3 cubed. That was a square. All right, so there would be the cleaned up answer of that derivative. That's it for today's lesson.